So in this video, we're going to talk about recursive sequences and proving whether they converge or not, as well as finding the limit. So let's look at the sequence. We know that the first term of the sequence is equal to 1. And we know that the next term of the sequence is equal to the square root of 3 plus the previous term of the sequence. And so by that definition, we can calculate the first few terms of the sequence, A1, A2, A3. So we know A1 is equal to 1. So we know that this A2 is equal to the square root of 3 plus the previous term, and the previous term is 1. So this is equal to 2. And A3 is equal to the square root of 3 plus the value of the previous term is 2, so the square root of 5. So how do we prove that the sequence is converging? Well, so some guy invented this theorem, and it basically, and it's called the monotone, I think it's just monotone sequence theorem. And basically what it states is that if a sequence is monotonic, and what monotonic means is basically that it's strictly increasing, so it's only increasing, or decreasing. So it effectively, as the name implies, only has one tone. It's only going to go up, or it's only going to go down. And if it fulfills the second criteria, that the second criteria that this sequence is bounded. And what bounded means is it has a maximum value and a minimum value. So the monotonic sequence theorem states that if it is monotonic, meaning that it's only increasing or only decreasing, and that it's bounded, meaning that it has a maximum and a minimum value, which we call the upper bound and the lower bound respectively, then we can say by the monotone sequence theorem that this sequence converges. Now, how do we prove that a sequence is monotonic, and how do we prove that the sequence is bounded? So proving that it's monotonic is kind of vague, right? Because, like, is it increasing or is it decreasing? So usually what we prove is that the sequence is strictly increasing or that the sequence is strictly decreasing. So looking at our values here, it looks like, just from what I can see, 2 is bigger than 1, and root 5. So it looks like, and I suspect, that it's an increasing sequence. So I currently suspect that it's an increasing sequence. I don't know yet, and that's what my proof will tell me. And then I'm going to guesstimate a bound. It looks like, well, I guess since I have a square root here, the minimum value that an could be would be 0. So my lower bound, I'm going to guess, is 0, and my upper bound, I'm going to guess is 4. So why did I guess 4? By looking at it, It doesn't look like it'll exceed 4. But if it does, once again, my proof will let me know. And so
talking through what you did and why you did.
And so in order to prove both of these facts, we use what's called proof by induction. Proof by induction basically states that if something is true for the base case, so for the first term, and if it's true for the a-nth term, so every term after, then it must hold true for all terms, which makes sense, right? Because if something is true for the first term, and it's true for the next term, and it's true for the term after that, then, and it's true for the terms after that to an infinite number of terms, then it should be true for all terms. And so let's first prove that the upper bound of the sequence is 4, or that the upper bound is 4, I guess. It doesn't have to be the lowest upper bound. My upper bound may be a number greater than 4, but what I'm saying is that my upper bound is, my upper bound can be at least 4. So to prove that an is greater than 4, an is less than 4, because my upper bound indicates that my an terms shouldn't exceed it, I'm going to prove the base case. So the base case is just a1. a1 is equal to 1, as we remember from the beginning. So a1 is just equal to 1. 1 is less than 4. So we can say that I've proven the base case for an is less than 4. Now the next thing we want to do is prove the an case. The an case is an. So we're saying that if my current term is less than 4, then I want to prove that my next term will also be less than 4. So if an is less than 4, then 3 plus an will be less than 3 plus 4, and the square root of 3 plus an will be less than the square root of 7. The square root of 3 plus an, as we've defined here, so if the square root of 3 plus the previous term is the current term, then the square root of 3 plus the current term will be the next term. And we indicate that it's the next term by calling it an plus 1. An plus index, we're not adding 1 to an, but rather we're indexing that it's the next term. This is less than root 7. We know that root 7 is less than 4. So we can say that if we know the current term is less than 4, then the next term will also be less than 4. So here we've proven the an case. From here. So now we want to prove that the sequence is strictly increasing. And when a sequence is increasing, what we know is that the next term, so not the next term, but the current term is greater than the previous term. And if the current term is greater than the previous term, then we want to prove that the next term will be greater than the current term. So first, let's prove the base case. The base case would be A1
just happen to know that that's
is equal to 1, which is,
so I think you got this one right by a lot.
oh, I should write this the other way.
So when we're trying to solve for something,
So A1
often we got to try to get that thing.
A1 is equal to 1,
Everything
which is less than 2, which is equal to A2.
as soon as we try to find
We had found A1 and A2 up here, and so we can say that the base case is satisfied because 2 is greater than 1, so A2 will be greater than A1. Now to prove the A term, if we assume that the current term is bigger than the previous term, we want to prove that the next term is larger than the current term. And so, like what we did with the upper bound, we're going to add 3 to both sides. And then we're going to square root both sides. And then this, by definition, is equal to the next term, so an plus 1. And this, by definition, as we see up here, by the definition of this sequence, an equal to the square root of 3 plus an minus 1 is equal to the current term. So we're saying here that if the current term is greater than the previous term, then the next term will be greater than the current term, which indicates an increase in the value of the terms, which indicates that it's an increasing sequence. And so now we've proven that it's monotonic because it's only increasing. And then we've proven its upper bound. The lower bound will, by induction, we can also prove that the lower bound exists. And so by the monotonic sequence theorem, we can say that this sequence converges. Proof of the lower bound, proof of the existence of the lower bound by proof by induction as an exercise to the viewer. But here we can say that this sequence, once we prove the lower bound, we can say that this sequence will converge. Not quite, because there's also so we still don't know what the sequence converges to, which is a bit of a bummer, because we want to know what the sequence is converging to. So let's rewrite an is equal to, so the current term is equal to 3 plus the previous term. And so once we know that it converges, the definition of converges means that the value of an has stopped changing once you hit a convergence term, right? So once the value of an stops changing, the next term, we can say that at the limit, the current term is equal to the previous term, which is equal to the next term. If we call this the limit, if we define when the current term is equal to the previous term as the limit, then we can make a substitution into our sequence term definition and say that the limit is equal to the square root of 3 plus the previous term. So the current term, which is the same as the previous term, is equal to the square root of 3 plus the previous term. And then from here we can solve for L by rearranging. So we get L squared minus L plus 3, minus 3 equals to 0. And we find that L equals to 1 plus minus square root of 13 over 2. Now we have two values for L. We have L equals 1 plus the square root of 13 over 2, or 1 minus the square root of And we know that this is a negative number. But we also know, if we remember from before, the exercise left up to the viewer is that we had proven that our lower bound is equal to 0. And so if our lower bound is 0, then it means that our sequence can never go below 0. And negative numbers are obviously below 0. And so we can say that the limit cannot be negative and it must be equal to 1 plus the square root of 13 over 2. So that's the limit of the sequence defined by a1 equals 1 and an equals the square root of 3 plus an minus 1.